Next, let's derive a formula for the distance from a point R to a line L. And of course, R is not on the line. So write this all down. Well, this is our goal. Derive a formula for the distance from a point R to a line L. And using vectors, of course. So you have a line. Let's draw the picture of that. So you have some line L, like this. Okay. And then you have some point. So you got a picture, if you have a line L, you're given the equation of the line. And in this case, you're given the equation of the line in 3 space. So it'll be essentially a parametric equation. So you can determine any point on the line. All right, then you have a point R. Okay, we'll call that R not on the line. And so what we may create is you take any point, say P, on the line, and another point Q on the line. So if you're given a line, you can find 2 points, no problem. Right? So that's the idea. And then what we're going to do is construct these vectors. We're going to construct the vector PR, like that. And we're going to construct the vector PQ, like that. Okay, so trying to fill that in a little bit. And so we want to find this distance. So our goal is to find the distance from R to the line. And it's assumed to be, the perpendicular distance, the shortest distance. So do we see that that's basically a triangle, right? So we have that triangle that we want to calculate the distance D. Let me change that color. So we want to calculate D. So if we have 2 vectors, we will know that there's an angle between them. So we're going to kind of work towards finding a formula that does not have theta in it. But first we'll start with that. And what's the trig formula to find D? Do you sine, cosine, tangent, cosecant, right? Well, you know that sine theta is equal to what? Well, that is opposite over hypotenuse. So the hypotenuse is the distance of the length of that vector. So how do you calculate the length of this vector PR? Well, you'll do magnitude of PR. Okay, so that means what we want to do then is define some vectors. So we're going to come over here, we're going to say let P and Q be points, on L, and let theta be the angle between the vectors. Theta be the angle between PR and PQ. So we'll construct those, assume those vectors we could create, PR and PQ. So we're going to do the magnitude of PR right here. And then we can solve for D. So D is going to equal magnitude of PR sine theta. All right, so one of our goals, and I'll put it down here, is we want to get sine theta out. We don't want to have sine in there. We want it out of there. So what we use is that other formula from the previous section. So we use that magnitude of PR cross PQ is equal to magnitude PR magnitude PQ sine theta. And so we can substitute that in to get our result. So basically then we can rewrite that as, let me show you. So what we have is this. So here's your PR, and here's sine theta. So here's PR sine theta. So we can substitute PR sine theta and write D instead. Right, so what's in purple? We just put D. So we make that substitution. So you end up with magnitude PR cross PQ is equal to D magnitude PQ. Right, because that is, so this and this is D. Okay, then you just divide out your magnitude PQ and you have your formula. So if you divide out D, it's equal to magnitude PR cross PQ divided by divided by magnitude PQ. So see what PQ is though? So here's PQ, but anytime you're given a line, you can just use the direction vector. So we can just replace PQ and just that you always know you're going to have the direction vector. So that's really the formula we want to use. Although it's the derivation that really is what I want you to focus on, is the entire derivation. So that's equal to magnitude PR cross V, the direction vector, over magnitude V. V, where V is the direction vector. Okay, so focus on how would you derive it and write it up. That's a really important aspect of this question. And we're writing everything in terms of vector operations. So this is only vector operations, and then we basically get out the theta. We want the trig concepts out of there. We're using trig to get to our result, but this is what we want to get to. So all vector operations. Okay, let's do an example. Okay, so here's an example. So find the distance from the point given, so point, I'll say R, to the line. Okay, so this happens to be number 36, by the way. Okay, so R is 2, yeah, 2, 1, negative 1. And the line given is x equal to 2t, y equal to 1 plus 2t, and z equal to 2t. Kind of makes it nice, I suppose. I'm noticing here you have 2t, 2t, and 2t. So really, that's just the direction vector 1, 1, 1. Kind of makes it simple. So, because t is anything, so that constant's the same. So what we basically are using, or what we can do, is just this parallel line, something like this. So when they're parallel, so you can make that as 2 times the 1, 1, 1. And so we can just use the 1, 1, 1 as our direction vector. Okay, so what we need to do next is, so you have some line. So let's talk through it. So you have some line, okay? And basically, we started with this direction vector, and I just made it a that direction vector. Okay, no big deal there. Okay, so the point R is up here, somewhere. There's your point R. And I have my direction vector. Okay, let's go ahead and change colors so you can see what I'm doing here. So I have some direction vector that's given. And so to construct this vector from the line 2R, I need a point on the line. So we need to find a point on the line. And that's one of the critical things. So how do you find a point on a line? So I'll write this over here. So find P, a point on the line. So the easiest way to do that is choose a value for t. So if I choose t to be 0, you could choose it to be pi, 1/2, 2/3, it doesn't matter. Then you calculate a point. But if I choose t to be 0, then I substitute back into my formula. I get 0, 1, 0. So my point, simple point P then is 0, 1, 0. And then calculate PR, which is then given. So it would be, where's R again? So 2 minus 0 is 2. And then you get 1 minus 1 is 0. And you get negative 1 minus 0 is negative 1. So we'll use the vector 2, 0, negative 1. So that's my P down here. And so you had to calculate that vector. So now you have to, now you have the components for the formula. So D is the, well, I got to do the cross product. Let's do that first. Well, I'll just write it out. So it's magnitude of PR cross the direction vector, which was, where's the direction vector? Which is 1, 1, 1. So it's cross V. And then it's over the magnitude of the direction vector. Well, that's just going to be root 3. So I got to do the cross product. I got to do the cross product of 2, 0, negative 1 cross 1, 1, 1. So I do that cross product, that's going to equal I, J, K, 2, 0, negative 1, 1, 1, 1, and I do that cross product. So that something like this, you can do it on your calculators, straight up, real easy, or do the calculation by hand for practice. Okay, so you get 1, negative 3, 2. And then you got to do magnitude of that. So you got to do magnitude of the cross. So it's magnitude of 1, -3, 2. When you do that magnitude, you get 1 + 9 + 4. So it's the square root of 1 + 9 + 4. So 14. So it's root 14. So that means the distance d from the line, so down here, line to the point to the line, is root 14 over root 3. And that's good enough for me. That's fine right there. You can get an approximation if you want, but that's it. Okay, so there's a good application of it. Know how to derive it or something similar. And that's what we need for that section. Okay, planes are next.